Welcome to the third lecture of analysis of several variable, and today's lecture we are going to discuss the fifth topic of module 1 is equilibrium, inner product and norm in Rn. So previously we covered this four topic, and today's topic, as we say, that equilibrium inner product and norm in Rn, and the fifth last topic is left with the continuity of functions on open subset of Rn. So let's start with the fifth topic, the equilibrium inner product in Rn. So we start with the inner product definitions. So here we take VB a vector space. So we are giving a general definition which is also applicable on the vector space Rn and any vector space. This definition is all good. So a function is V cross V, means two variable functions to the real number R is said to be inner product if for u v w belongs to V from the vector space V and alpha is from the scalar or from the field R, then if it satisfied following properties, then we call its an inner product. So first property is that VV means if we take same vectors, same vector from this V cross P, then we will have that this is greater than equal 0. And the equality holds only when V is equal 0. That means it is on the same line. Means if you take this cross product in this way, so the vectors which is on the same line, y is equal x. So in this line, the cross product will be always non-negative and the 0 happen at origin only. Second is the property is VW is equal WP, means if you change the position of the vectors, then their inner product will be same, means this function's value should be same. So the third property is known as the distributive property, which is says that u plus v w is equal u w, the functions u w plus the function v w, means you can separate this part and then this equality happens. And fourth one is that if alpha v and alpha is an scalar and w, then the scalar can be go out and then it will become alpha the function v w. So in this case we will note here that if it is alpha v plus beta w, then alpha will independently come out, beta will independently come out, and then you will have here v w. Same way, in this case, if it is, let's say, u v plus w, then it will be uv plus u w. So this distributive properties and this scalar multiplication property will happen with any position of the this function's entry, either first one or second one. So if a vector space satisfied with all these four properties and have this function, and with a vector space with all these properties and a vector space with this function and satisfying all these four properties is known as inner product space. And now one basic question is that does the inner product and dot product are same? So we'll see that after few slide. Okay, now we have here one example or one problem. Let's say v is equal r2 and the functions in is defined as like this: a b c d, which is 3ac plus 2bd plus ad plus bc, and then the question is there, so that this function, given function, is an inner product. So let's have the solution here. So we have to verify all those four properties we discussed in previous slide. So we'll do it one by one. So first we'll say v is equal ab and w is equal cd, and for later purpose we will take it u is equal, say, x y. Now it says that first property will have v, this should be greater than equal 0. Now in this case what it will be, the definition of vv, which is ab a b. Now here is definition is 3ac, that means first of both vectors. So first entries, so in this case first entry is a, so this will become 3a square. Second entry is 2bd, means second entry, so it will become here 2b square. Then ad means first and second, so in this case it will be a b, and same way it will be b a. So now we can rewrite this one as 2a square plus b square plus a square plus b square plus 2ab. So this is equal 2a square plus a square plus a plus b whole square, so which will be always greater than 0. Now the equality of this 0 will happen. So clearly the equality holds if 3a square plus 2b square plus 2ab is equal 0. So which is true only when a is equal 0 equal. So therefore the equality holds if v is equal 0 0. Now we'll take the second property. It says that if you change the position, that is v w is equal w v. Okay, how we can prove this one? We start with the vw. So vw means we'll have a b c d, which is same as the definition. So 3ac plus 2bd plus ad plus bc. Now as a b c d all are real numbers, so we can rewrite that this is equal to ca plus 2dB plus BA plus CB. So this is by definition, you will see that CA. So therefore we can say C, and this is the inner product of C, and here it will be A, and this one is D, this one is P. So which is nothing but W. So we establish the commutative property. Now next we will have the distribute property. So it says that the third one says that U plus V W. So this is equal, in this case it will be X Y plus UV, and XY plus AB, and this is CD. Okay, so if we do this addition, so it will be X plus A, Y plus B, and then we have C, D. Now we will take it the definitions, which is 3AC. So it will be X plus A, and this is C, plus 2BD, Y plus B, D, plus AD, X plus AD, plus BC. So now we'll separate them with the XY and remaining terms. So first we'll take 3xc plus 2yd plus xd plus yc, and then remaining term is 3ac plus 2bd plus ad plus bc. So if you notice from the definition, so this will be the one functions with xy and cd. This is another function. So we can rewrite this. This is inner product xy and cd plus ad and cd. So this means xy, so that means inner product u w plus inner product ad. Ad is v, this is w. So we prove the third property. Next is the fourth one. Fourth one is we multiply by scalar. So alpha v w. So this is equal alpha ab cd. So this is equal alpha a, alpha b, and cd. So this is 3 alpha ac plus 2 alpha bd plus alpha ad plus alpha bc. So we can take out this alpha and we'll get 3AC plus 2BD plus AD plus BC. So this is equal alpha inner product AB C D. So this is equal alpha V W. So we complete the proof. So therefore, given is an inner product. Okay, we have the next problem, and in this problem we have to show that this is an inner product. So we'll do it as in the previous problem. So first we'll take that V is equal AB, U is W is CD, and U is X, Y. So the first property is V. So this will gives you AB. So AC means the first and first. So this is A square plus B square, which is greater than equal 0. Clearly A square plus B square is equal 0 if and only if A is equal 0, B is equal 0. So this implies B is equal 0, 0. So this verify the first property. Second property, VW. So this is AB, CD. So which is AC plus BD. Now if we take WB, this is equal, we'll have here CD and AB. So this is again CA plus DB, which we can write it AC plus BD. So this is equal VW. Okay, now we'll have the third property is U plus VW. So this is equal X Y plus AB and then C. So this is equal X plus A, Y plus B and C D. So this is equal X plus AC plus Y plus B D. So this is XC plus YD plus AC plus BD. So this is inner product U W plus this is inner product B W. So therefore the third property also holds. Now we will have the fourth property, which is very easy, is alpha U W. So this is equal alpha A, alpha B and then C D. So this is by definition alpha AC plus alpha BD is equal alpha AC plus BD. So alpha inner product inner product VW. So this establishes this inner product. Then we'll see that here This is known as the dot product. Therefore, we will have inner product we have here, sorry, dot product on Rn is an inner product. If we a vector space over a field R, a function this notation V cross V to R is said to be norm if for u V belongs to V, alpha belongs to R. This function satisfies three properties: is norm of V is greater than 0 and norm of V is equal 0 if V is equal 0. This is called the positivity. And alpha V is equal absolute value of alpha. This is called scaling. And third one is the known as the triangular inequality. So in this aspect, what are the norms of Rn? Okay, so if we have these sets, then B and be a vector space. Okay, let V is equal V1, V2, Vn be a vector in Rn, and the norm V dash is given by this V2 is equal square root of V1 plus V2 plus Vn as a component wise addition. Okay, there are other norm or Rn defined as follows. That norm of V1 is equal absolute value of addition of the absolute value of the each component, and then we'll have Vp, so which is power absolute value of xi power p over 1 over p, and V infinity is the maximum of the xi over the vector given vector. So let's, if we have V is equal, just take one vector 1 2 and 0 4. Then in this case, norm of this V1 is equal 1 plus 2 plus 0 plus 4, so which is 7, and norm of Vp, this is equal xip, so that means 1 to the power p plus 2 to the power p plus 0 plus 4 to the power p, and then 1 over p. And the fourth one is, if we take V infinity, so this is the maximum of xi, so maximum here is 4, so maximum of 1 2 0 4, which is equal 4. All t belongs to R, define, so we are going to define a function, a special function, so which is pt is equal norm of tv minus u whole square. So before going to prove this, so we just find out this one. So norm of V whole square, which is actually the inner product of V So we can write it here, norm of PV minus U whole square. So which is inner product TV minus U and TV minus U. So therefore now we apply the distributive property of the inner product. So this is TV and then plus TV minus U plus minus U TV and then plus minus U minus U. So here T is a scalar, so we can take out T. So it will be T square and it will become V inner product plus here is minus. So first this minus and this T. So it will be minus T and then you will get inner product V. So same way here this one is T and this is U V and last one is U. So this will gives you T square norm of V whole square and then here you will have this is minus. So this is minus 2 T U and V plus norm of U whole square. So therefore PT is a polynomial of T of degree 2. Okay, so therefore P dash T is equal to T norm of V whole square minus 2 inner product U P plus norm of V whole square, so that will be 0. So therefore P dash P double dash T is equal to into norm V whole square, which is greater than equal 0. So now P dash T is equal 0 if 2T norm of V whole square is equal to inner product U. So this implies T is equal inner product UV over norm of V whole square. So therefore PT has a minimum at T naught. So therefore PT has a minimum T has a minimum at T naught. At T naught. So therefore PT naught is equal t square norm of v minus 2t inner product uv and plus norm of u whole square. So T naught is u p over uv over norm of v whole square norm of v whole square minus 2 uv over norm of v whole square u plus norm of u whole square. This is equal u p over norm of v whole square minus this is 2 uv over norm of v whole square plus norm of whole square. So if you simplify this, so this will become minus 2 inner product uv over norm of v whole square. This is whole square and this is whole square. So minus 2 uv whole square norm of v whole square. So this is whole square plus norm of u whole square. So now pt is equal norm of t v minus u, so which is greater than equal 0. So therefore minus uv over norm of v whole square plus norm of u whole square, this is greater than equal 0. So this implies norm of uv whole square is whole square is less than equal norm of u whole square. So this implies norm of uv over norm of v is less than equal norm of u. So this implies uv is less than equal norm of u multiply norm of. So this verify the Cauchy inequality.